Okay, so we're going to try and fit a linear model to a scatterplot. Now, we've got some bivariate data, we've got the relationship between height and foot length of some students. So we've got 9 students here, different heights and foot lengths. So it says draw a scatterplot first. Hopefully we're okay that usually we go X on top, Y on the bottom, so the height's going on our X-axis, foot length is going on our vertical or Y-axis. And it kind of makes sense a little bit more that this one here is our explanatory variable, and that the foot length is in response, so this is our response variable to your height. So I'm going to press on and let's describe in terms of strength, form and direction the relationship. So just having a look here, if we roughly put in a trend line, I'll probably say it's a fairly strong relationship. It could be moderate. We'll have a look at that a little bit later on. Form is linear, and a positive relationship because it's going up as we go from left to right. As one gets bigger, the other one gets bigger. So now we move to determine the least squares regression equation, or it's sometimes just called a trend line, the linear trend line, for that data using your calculator. So on Excel it's pretty easy. On Excel you just click on the trend line and you say display the equation on the chart, and you can put your R² value in as well. But in an exam situation you don't have access to Excel, so what we do is we get out our calculator and we are going to enter it in stat mode. So to do that, we're going to start off by pressing mode and then 2 for stat. Now the option that we want here is the option 2, which is our bivariate data. So it's got A plus B X. That is the one that we want. And we can enter in all of our data. So just pressing in each height to start with, and pressing in enter at the end of it. And once you've done all of that, you need to press AC. So I'm going to quickly put in the rest of these. So scroll up and 30, so on and so forth. Okay, got all 9. Now we press AC. Should see the level stat thing at the top here. And now to get it to use the stats, we're going to go Shift, then 1. You can see the little stat above that in yellow. And we're after the regression equation. Now we've got a couple of options here, or a few options. We've got an A value, a B value, and an R value. Now we're going to use 3 of those in a moment. So if we start off with, it said there before it was A plus BX. Now that is very similar to what we're used to be using in junior, which was Y equals MX plus C, which hopefully we know is the gradient, is the M, and the C is the Y-intercept, where it crosses the Y-axis. So when it's Y equals A plus BX, the gradient is your B, the X coefficient, and the Y-intercept is the A part. So we can write the equation for this with the data that we've just entered by pressing 1, which gives us negative 20.28699. So negative 20.2869. We go dot, 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 it keeps on going, plus B. Now B we can find as well. We go AC, Shift 1, 5 for regression again, and we're going to go to which is 0.2632, 0.2632 dot, 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 lots of X. So that's our B in front of our X. So that's that is the equation for that line of best fit. You could also write it in Y equals MX plus C form, which would look like this. Doesn't really matter which way around you do it, as long as the number that goes in front of the x is that b value that you found, and the a value goes there with the negative 20. Determine the r value. So our r value we can also get from our calculator. So if we go shift 1, 5, and 3 for r value. So that's our Pearson's correlation coefficient. And we've got 0.897, so on and so forth. Now what that says is that it is a strong relationship. So it confirms that it is a strong relationship. Remember that a strong relationship will be an R value between 1 and 0.75 is strong. 0.5 to 0.75 is moderate. 0.25 to 0.5 is weak. And going down to 0, there's no correlation there. Now we can have a negative R value, so that keeps on going down here if it's between the negative versions of that. So negative 0.75 to negative 1, that's a strong negative relationship. Okay, so that R value can be negative all the way down to negative 1. So just be careful with that if you see that there is a negative gradient. So determine the coefficient of determination, the R squared value, and use the sentence to describe what it means in this context. The R squared value is just the R value getting squared. So the answer squared there. So our R squared for this one is 0.8047, I think it was, just double check, 49. So we notice that that goes down a little bit, and that always will happen. That it will go closer to 0 when you square the R value, and so it'll always be positive as well, the coefficient of determination. So using the sentence to describe what it actually means, that means that 80.49% of the variation in the y-axis, and on our y-axis here is foot length, of the variation in foot length can be explained by the change in height. So generally, as students get taller, their foot length gets bigger, and that's 80% of the reason for that is simply because of the change in height compared to the change in foot length. The other 20% could be for other reasons. Okay, it could be sort of genetic reasons or whatever it might be. Okay, so the next thing we're going to do is we're going to actually use that trend line to determine the height of someone who is 179 centimetres tall. So if we did have our trend line, we've got a rough trend line here, we could do what we call interpolating. So we go 179's here, rule it up over there and rule it across. Oops, should use a ruler for that. Being a little bit lazy there, but we're thinking, yeah, around about 27 centimetres of foot length. That's a very, very rough trend line and a very rough interpolation. Now remember, interpolation means making predictions using the trend line within the data range, so from here all the way down to here. Extrapolation, that means extending the line of best fit out and making predictions further on, okay, or extending back this way and making predictions for shorter people. So now this one says use the trend line to do this though. So what we're going to do is we're going to use this trend line that we worked out over here to work out what we think that trend line will be. So we've got an x value, because it's a height, we've been given a height of that. It's an x value is our height of 179. And we're going to stick it into the equation. Now, I'm not sticking into the bottom one, so 0.8047 2632. It doesn't matter because they're both the same equation, but that number going on and on times by x, so we've got an x of 179 minus 20.2869. And that we can just stick in on the calculator. Here. So 2632 times 179 minus 20.2869. We've got 26.825 centimetres. So it's a foot length of around about 27 centimetres. Okay, if we're rounding that, which is around about what we thought, you know, with that fairly rough trend line that we had there before. Now the next one is to use the trend line to predict the height of someone who has a foot length of 47 centimetres. So that's actually, I looked that up, the foot length of the tallest man who ever lived. Now what that's saying is that's a y value now of 47. So we've got our equation y equals 0.2632, so on and so forth, x minus 20.2869. So we're saying at y equal to 47. So basically, we can rewrite that equation, but instead of writing y, we're going to put 47 in there, sub it in. And now we've got an equation that we've got to solve, and we solve by looking at x, and we say what's happening to x. X, first of all, is getting times by this. It's then having that subtracted from it. So our first step is to get rid of the subtract 20.2869 blah blah blah, and we do that by adding that to both sides. Now, so that's going to give us 67.2869, so on and so forth, is equal to that. Okay, so those disappear, that cancels out. And now we've got x times by all of that. So we've simply got to divide both sides by that. Okay. And so x is going to be whatever we've got here. We'll bring that up on the calculator, 67.2869 divided by 0.232, 255.64. Centimetres is the height of Robert Wadlow based on that, 256 centimetres, which is very, very tall, but it's actually not as tall as he was. I think he was 2.72 metres tall. But we are extrapolating with this data, so that probably not as accurate when you're extrapolating. Interpolating, you are going to get a higher level of accuracy. We've got a reasonably good R value to say, well, that is a reasonable value to get for the height of someone who has such a big foot, okay? So it is a reasonable answer in that respect, even though we're off by, yeah, a bit under 20 centimetres. So, yeah, that's sort of how you can use your calculator to get a least squares regression line, and then how you can use that line to do that. So further exercises like this, get exercise 2.3 in your text.